What if the ultimate bottleneck for the future of artificial intelligence isn't silicon chips, brilliant algorithms, or massive data sets, but a silent, towering concrete relic from the height of the Cold War? Right now, the world's richest technology giants are quietly buying up retired nuclear reactors, because training the next generation of frontier artificial intelligence requires an ultra-reliable power source that can never, ever blink. Welcome to the front line of the clean energy gold rush, where the digital cloud is crashing headfirst into the physical realities of the atomic age. To understand the scale of this crisis, we have to look inside the modern data center. Picture a standard search query. It is incredibly quick, requiring just a tiny burst of electricity, about enough to light a single LED bulb for a few seconds. But generating a single response from a state-of-the-art AI model, that requires up to 10 times more energy. Now multiply that by the millions of people using these tools every single hour. The results are staggering. Every single prompt you type triggers a massive cascade of calculations across thousands of specialized graphics processing units, or GPUs, humming inside football field-sized warehouses. These microchips run hot, and they run continuously. They are the engines of the digital renaissance, but they have an insatiable, physics-defying appetite for electricity. Think of a modern AI data center not as a storage warehouse, but as an industrial smelting plant. A single modern, massive AI data center facility can consume over 100 megawatts of electricity. That is enough to power 80,000 average American homes. And the tech giants aren't building just one or two of these facilities. They are building hundreds of them simultaneously across the globe. By the year 2030, data centers are projected to consume up to 9% of the entire United States electricity supply, nearly doubling their current share. Globally, the energy demand from these digital hubs is expected to equal the total electricity consumption of entire nations like Japan or Germany. This creates a monumental, historic conflict. Tech conglomerates like Microsoft, Google, Amazon, and Meta have spent the last decade positioning themselves as champions of environmental sustainability, promising to achieve net zero carbon emissions. They cannot simply build massive new coal-fired or natural gas-burning power plants to feed their hungry server farms without destroying their climate pledges. But they also face a brutal reality of electrical engineering. Wind and solar power, while clean, are highly intermittent. The wind does not always blow, and the sun inevitably sets every single day. To keep a traditional website online, you can rely on a mix of renewables and grid batteries. But training a frontier AI model is a completely different beast. Imagine a training run as a massive, hyper-complex puzzle being solved by a team of 100,000 workers who must all pass pieces to each other in perfect synchrony. This process takes months of continuous, uninterrupted computation. If the power drops for even a fraction of a second, the entire synchronized state of the system collapses. The memory stored in the GPUs is wiped. Progress is corrupted, and millions of dollars in compute time vanish instantly. To prevent this, AI training operations require what grid engineers call 5 nines reliability, which means an uptime of 99.999%. They need baseload power, clean, continuous, and completely unaffected by weather or time of day. And there is only one clean source on Earth. This is why tech giants are suddenly obsessed with dead nuclear plants. Imagine a sleeping atomic giant. In Pennsylvania, sitting on the Susquehanna River, lies 3 Mile Island. While Unit 2 of the plant was the site of the famous 1979 partial meltdown, its sister reactor, Unit 1, operated safely and flawlessly for decades. However, in 2019, it was shut down early, not because of safety issues, but because cheap natural gas made nuclear power economically non-competitive. It sat silent, its massive concrete cooling towers looming over the landscape like monuments to a bygone era. But in September 2024, Microsoft shocked the energy sector by signing a massive 20-year deal with Constellation Energy to fully resurrect this dormant reactor. Renamed the Crane Clean Energy Center, Microsoft is purchasing 100% of its 835 megawatt output. This marks the first time in history a retired American nuclear plant is being brought back from the dead solely to power a single company's digital empire. But why go through the immense hassle of restarting a dead nuclear plant instead of just building a brand new one? The answer lies in the grid's hidden bottleneck, the interconnection queue. Think of the modern electrical grid as a hyper-congested highway system. If you build a new power plant, you cannot simply plug it in and start selling electricity. You have to wait in an endless administrative line to get permission. In the United States, this queue is severely backlogged. It can take up to 7 or even 10 years for a new project to receive approval, clear environmental impact studies, and pay for the necessary high-voltage grid upgrades. But a retired nuclear plant is different. It already has its spot on the highway. The physical high-voltage transmission lines, high-voltage substations, and legal connections to the regional grid are already in place. This permits tech companies to bypass years of red tape, slashing the timeline to get clean, reliable power online. To maximize this advantage, tech companies are utilizing a physical setup known as behind-the-meter co-location. Instead of sending the electricity from the nuclear plant onto the public grid and drawing it back down at their data center, they are building their server farms directly adjacent to the reactors. In early 2024, Amazon's cloud division, AWS, purchased a newly constructed data center campus in Pennsylvania for $650 million. This campus is situated directly next to the Susquehanna Steam Electric Station. Amazon is plugging its server racks directly into the nuclear plant's physical output. By doing this, Amazon bypasses the public transmission system entirely, avoiding local distribution fees, grid congestion, and the risk of regional blackouts. It is an incredibly secure, private bubble of pure, infinite atomic energy. However, this private atomic land grab has sparked a fierce public backlash. When tech companies buy up existing clean nuclear power for their private servers, they are effectively taking that clean energy away from the public. Picture a town where a wealthy tech developer buys up the local water reservoir. The developer gets all the clean water they want, but now the townspeople are forced to pump from dirtier, more expensive backup wells. This is the exact concern raised by utility regulators and consumer advocates. If Microsoft and Amazon monopolize the nation's cleanest baseload power plants, local utilities will have to run their aging coal and gas plants longer to keep the lights on for average households. This could drive up monthly electricity bills for everyday citizens and increase carbon emissions, negating the very environmental, carbon-free progress these tech companies publicly. This growing tension escalated into a major regulatory showdown in late 2024. Major utility companies like Exelon and American Electric Power filed official complaints, arguing that Amazon's co-location deal at the Susquehanna plant would unfairly shift transmission costs onto everyday utility ratepayers. In late November 2024, federal energy regulators sided with the critics, blocking a key power-sharing agreement and throwing a wrench into Amazon's nuclear strategy. This regulatory roadblock is forcing tech giants to look beyond old reactors and fund a radical new frontier: small modular reactors, or SMRs. Instead of building massive, multi-billion-dollar nuclear facilities that take a decade to construct, startups are designing miniature reactors that can be mass-produced in factories, transported on flatbed trucks, and assembled directly on-site at data center campuses. The momentum behind SMRs is building rapidly. Google recently signed a groundbreaking agreement to purchase power from a fleet of small modular reactors developed by Kairos Power, aiming to bring them online by 2030. Not to be outdone, Amazon announced a major investment in X Energy to deploy SMRs near its massive operations. These futuristic reactors use advanced molten salt or helium gas instead of water, making them inherently safer and more efficient. Yet, a massive catch remains. Not a single commercial SMR is currently operating in the Western world. The technology remains highly experimental, faces rigorous oversight from the Nuclear Regulatory Commission, and requires a specialized fuel called high-assay low-enriched uranium, or HALEU. Currently, the primary commercial supplier of this fuel is a Russian state-owned enterprise, creating a critical geopolitical bottleneck. Tech giants are placing multi-billion-dollar bets on an unproven nuclear technology and a supply chain that has yet to be built. We are witnessing an extraordinary convergence of human ingenuity. The most advanced, ethereal software we have ever written, deep neural networks capable of logic, creativity, and reasoning, is now directly dependent on the heavy industrial physics of splitting atoms. The ultimate, long-term winner of the AI race will not be decided merely by who has the most elegant code, but by who secures the most gigawatts of reliable, clean electricity. If these massive bets succeed, the tech industry's insatiable demand for power could fund a global nuclear renaissance, solving grid issues and proving clean energy technologies that could help save our planet from climate change. But if they fail, we risk destabilizing our existing power systems and raising costs for millions of people. The next time you ask an artificial intelligence to write an essay or generate code, remember the invisible reality humming silently behind the screen. Miles of heavy copper cables, towering concrete domes, and the blinding, silent heat of splitting uranium atoms, fueling the mind of the machine. The future of intelligence is heavy, hot, clean, and atomic.